All right, welcome to section 2.3, applications of circular functions. We're going to look at now this arc length, where we've been talking about the length s of the arc intercepted on a circle of radius r by a central angle of measure theta radians is given by the product of the radius and the radian measure of the angle. So s equals r times theta, where theta has to be measured in radians. All right, so let's look at an example here. A circle has a radius of 18.2 centimeters. It has an arc that's intercepted by a central angle having 3 pi over 8 radians. Since it's in radians, we just multiply those two values together. So I would go to my calculator and type in 18.20 times 3 pi over 8, or 3 times pi divided by 8. There is my answer. Rounding, since it was 18.202 decimal places, we'll round to 2 decimal places as well. Now again, as I mentioned in the previous video, if the directions tell you to use 3.14 for pi, then you change this to times 3 times 3.14 divided by 8. Otherwise, your decimal will be off because of the rounding error. Part B, now they give us a central angle in degrees. So when we set up our S equals radius times theta, we're going to have to take the 144 and multiply it to pi over 180 so we can get the degrees to cancel. So you can reduce this if you wish, or we can just go to the calculator. Again, enter everything in. 18.20 times 144 times pi over 180. We get 45.74 centimeters. Now again, if they want 3.14, you know what to do. Use 3.14 instead of the pi symbol. A really common distance between two cities problem is latitude gives the measure of a central angle with the vertex at the Earth center whose initial side goes through the equator and whose terminal side goes through a given location. Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40 degrees north, and Los Angeles is 34 degrees north. The radius of the Earth is about 6,400 kilometers. Find the north-south distance between these two cities. So it's basically saying, find the arc length. All right, so we're going to take 6,400. We're going to take the 40 minus 34 to get 6 degrees. And again, we have to multiply that by pi over 180 to convert this into radians. If you want to do some reducing here, 6 goes into 183 times, 0 and 0 cancels. So 640 pi over 3 kilometers. Now, there may be times in my math lab where they want you to leave the answer in terms of pi and also give a decimal answer. So again, follow the directions. If they don't tell us to use 3.14, then our calculator entry will use pi, and we get 670.2 kilometers. If you have to use 3.14, you know what to do. Use 3.14 instead of pi. All right, example number 3. Find a length using S equals R times theta. A rope is being wound around a drum with radius of 0.8725 feet. So we'll round everything here to 4 decimal places. How much rope will be wound around the drum if the drum is rotated through an angle of 39.72 degrees? So again, we'll have to convert this into radians. So there's my formula, there's my radius, there's my degrees being multiplied by pi over 180. Again, we're going to let the calculator do all the work. So again, make sure you write this out because this is exactly how you want to enter it into your calculator. And we are at 0.604855, round the 8 up to a 9 feet. Example 4, finding an angle measure using, again, our arc length. Now what's very interesting here is you have a small gear that's driving a bigger gear. So if the small gear has a radius of 2.5 centimeters and goes through an angle of 225 degrees, through how many degrees will the larger gear rotate? Now, the nice thing here is you do not have to convert these into radians because the answer says in how many degrees will the larger gear rotate. You don't need to convert to radians. So this larger gear, I'm going to extend that radius to a diameter and cut right into this center and use this as my initial side, and that's approximately my 225 degrees right here. So I'm going to kind of shade in those gears right here. That's my arc length. That's how far small gear 1 is going to go. Well, what must be true is these gears come together. This golden arc right here has to be the exact same distance on the bigger gear. The problem is it's not going to be a bigger angle. It's going to be something less than 180, which makes sense. Now, both those arc lengths being the same, all we have to do is find our second theta, our second central angle, and that's what we're looking for. But again, since the arc lengths are the same, we're going to work with two formulas here. So my first gear, that's r sub 1 times theta sub 1. That's this arc right here. That's this s. This same s is this arc right here, which is going to be second radius, 4.8, times our unknown central angle. So if we plug in our information, 2.5 times 225 degrees equals 4.8 theta sub 2. All you have to do to solve for theta sub 2 is divide over the 48. And now we can go to the calculator, type it all in. 2.5 times 225 divided by 4.8, 117.1875 degrees. Now to verify this, if I take, this is the exact value. So if I go to my calculator and I find the arc length, so I got to change this to radians, I get 9.817477042. I take the 4.8 times 117.1875 degrees times pi over 180 degrees. Ta-da! Both arc lengths exactly the same. Now, be on the lookout for these types of these gear problems here. I want to give you some hints. Don't be surprised if they take this gear attached to this gear, to another gear, to another gear, to another gear. All you have to do is take the first gear and set it equal to the last gear's arc length. You don't have to go gear to gear to gear to gear. Now the other thing, pay attention on the bicycle problems. Let's say this big gear is where your pedals are at, and there's a chain going back to the smaller gear on the back tire. Okay, and then they also give you the radius of the tire. Now, because those two share the same axle, it's not about arc length. You will want to find the theta of the small arc and then take that exact same theta and multiply it to the radius of the big bike tire. And that will tell you how far you travel or how long the tire's been on the ground or however they ask the question. But that one is not setting one gear equal to another gear in terms of arc length. Next formula we're going to talk about is area of a sector of a circle. So a sector of a circle is the portion of the interior of the circle intercepted by a central angle. Think of this as a piece of pie. So this shaded region is my area. So our formula is area equals 1/2 r squared times theta, where again theta has to be measured in radians. It looks a lot like 1/2 times base times height, doesn't it? Because that kind of looks like a triangle. But again, let me emphasize this enough. What this is a portion of the circle. If you wanted to find the area of a circle, it is pi r squared. Here's my central angle. That's my pi, my 1/2. This is making a proportion, if you will, to create that formula. Okay, first example, finding the area of a sector-shaped field. The center pivot irrigation system provides water to a sector-shaped field with the measures shown in the diagram. Find the area. Okay, there's my formula. 15, whoops, we got to get this in radians, so we're going to have to multiply that by pi over 180. There's my radius. Enter everything in. We'll go to the calculator. Our approximation for the area of our field is 13,488. Let's see, where should we round to? 2 decimal places, 0.04. And that's going to be meters squared because there's my unit meters. That's the linear length. Area is always measured in square units. All right. So this section's a little bit longer